looking at these questions of computability, we first of all ask ourselves the question that are non-deterministic Turing machines more powerful than deterministic ones? So the answer is no. Every non-deterministic Turing machine can be fully stimulated by a deterministic Turing machines, but that's not the same case with push-down automatas. They are not equivalent, deterministic and non-deterministic. But in this case, they have exact same expressive computing power except the same languages. Like, how does a deterministic Turing machine stimulate a non-deterministic one? So a deterministic Turing machine uses multiple tapes to simultaneously enumerate and stimulate every single branch of non-deterministic choices of length whatever, accepting the input if any one stimulated branch accepts. So the machine uses selection tape like an index, for example, like 1 to 1, 1 up to 2, 2 up to 1, to sequentially test every possible timeline of events. So starting from 1 to 1, or maybe 1 to up to 2, and things like that. Now, what is the expressiveness of a Turing machine? Now, the class of languages accepted by a Turing machine is completely identical to the class of type 0 languages. So now a Turing machine can compute complex structural languages like a to the power n, b to the power n, c to the power n, which strictly matches the power of unrestricted type 0 grammars. So they are the least restricted ones. So they are very powerful. What is the Church-Turing thesis? It states that every effective computable function, meaning it can be computed by a finite mechanical process, is also Turing computable. So if a human can solve a math puzzle on paper using strict finite rules, a Turing machine can be programmed to solve it too. So everything that has an algorithm can be turned into a Turing machine. That's the Church-Turing thesis. Why can't the Church-Turing thesis be formally proven? So it cannot be proven because effectively computable is an intuitive notation rather than a strict mathematical theorem, like, though it has remained perfectly consistent with all computation models since 1936. You cannot write a mathematical proof of an intuition human thought. You can only observe that no one has found an counterexample in nearly a century, meaning that we believe this because it has been consistent and there has been no algorithm that you have made which you cannot make a Turing machine of. So you cannot imagine of what you cannot imagine of. If you cannot even think of something, then you cannot prove it, basically. So if you cannot think of an algorithm that doesn't make of a Turing machine, then basically you cannot prove it. But that doesn't mean that the Church-Turing theorem is wrong. That just means that you cannot think of it yet. And it's based on your human thought and intuition that if you can make an algorithm, you can just convert it into a machine using steps. Basic common sense. Now, what is this decision problem? So now we have decidability and undecidability. It is strictly yes-no problem, such as asking if a graph is connected or if a program will enter an infinite loop. So it's a yes or no question, and based on that, if a program will enter an infinite loop or not, based on the answer. Asking if 7 is a prime number, if a decision problem because the only valid outputs are yes or no. Yeah, this is a decision problem because you only have two answers, yes or no, and this is a decision problem. Now, what is the difference between decidable and semi-decidable? A problem is fully decidable if an algorithm can compute both yes and no answers. It is semi-decidable if an algorithm is only guaranteed to compute the yes answers. Now, you can fully decide an algorithm, both yes and no answers, but it is semi-decidable if it is only guaranteed to compute the yes. For example, a fully decidable program guarantees a no if a file doesn't exist. So if it's not a prime, then it will say no. While a semi-decidable program might just freeze forever searching for it. So it will keep searching, and it will never say no because it just never learns to say no. Now, how does decidability relate to semi-decidability? Now, a language L is fully decidable if and only if both languages and its complement are semi-decidable. Example is that if you have one machine that finds all yes answers and another finds all no answers, running them together guarantees a final decision. So there is a machine that finds all yes and another one that finds all no. Running them together at the same time will definitely yield you a final decision, yes or no, because he all finds all the yes, he also finds all the no's, and then there needs to be a final, otherwise they will never finish. So decidability does relate to semi-decidability. Why must undecidable problems exist? There are only countably many Turing machines presented by the Gödel number, but there are uncountably many languages. The power of the set, whatever, meaning there are mathematically more problems than there are programs to solve them. So there are infinite combination of decimals, but only finite combination of code to write programs. So some math problems physically cannot have a program because the numbers are infinite, and there are more problems than there are programs to solve them. That's also similar. Like, for example, is 7 a prime number? Then we have to write a program about it. But these are problems, right? These are questions. But there are very many of these because math is infinite, and we are programming now about it. We're looking at the solution after the problem. The halting and other undecidable problems is that what is the general halting problem? Now, Alan Turing 1936 stated that it is undecidable to determine whether a given Turing machine will ever terminate when given a specific input word. You cannot write a universal debugger tool that perfectly guarantees whether any given codebase will eventually stop or freeze forever. Meaning that you cannot ask a debugger that it will guarantee you that a code base will stop or freeze. It can never tell you that. So it can never tell that if something is going to terminate or not. And that's the same thing with a Turing machine. How does the ELK program prove the halting problem is still undecidable? So if an eternal loop checker ELK existed, you could write a paradox program, SCAMP, that intentionally loops forever if ELK says it will halt. So ELK says no or halts, then what SCAMP does is that it runs into infinite loop and halts if ELK says it will loop, creating a contradiction, meaning that it stops if ELK says it will loop. So if ELK wants to loop, then this stops, but that should happen first. It says no, then this goes into loop, and if this stops, it doesn't matter because it's already in the loop. Then it would have gone there, but it doesn't even go there. So if a magic software checker says your code will crash, you write code that intentionally stops safely, making the magic checker instantly wrong. So he says that it will not work, but you write it this way so that he is not wrong. How does the second variant matrix prove the halting problem is undecidable? If you list all the Turing machine inputs in a grid showing yes or no for halting, yes it halts, no it doesn't, you could create a new Turing machine that purposely does the exact opposite of the diagonal entries, proving a universal deciding machine cannot exist in that grid. So if you make a master list of all true predictions, you can build a robot that purposely does the exact opposite of its predicted row, breaking the list. Meaning that if you're able to create a list of true predictability, that oh yes it will halt, yes or no or whatever, but then you could create a new Turing machine that probably does the exact opposite. It does the opposite of what it's doing here. But this cannot be found here, of course, because it's doing the opposite. And proving a universality cannot exist in the grid. Now, you can always build a robot that purposely does the exact opposite of its predicted row. So we want to prove them wrong. We said he said he will do this, he will do that, he will do this. But wait a minute, we just inverted it and we did something different, and of course it will not do that anymore. And that's what we're doing. It won't do that anymore, which proves them wrong. What are some other examples of undecidable problems? Other undecidable problems include post correspondence problem, PCP, determining if the intersection of two context-free language is empty, and checking if a context-sensitive grammar generates an empty language. So you cannot write a program that perfectly checks if two entirely different context-free grammars will ever guarantee the same sentence. So if there are two context-free grammars, CFGs, two of these, and that are entirely different, they will not guarantee that it ever have the exact same sentence. And that's another reason why we can believe that these are other indecidable problems. Then we have to look into what is a busy beaver problem. If it asks to find a Turing machine with n states that writes the absolute maximum number of ones to a tape before halting, calculating the maximum number Bn is entirely unpredictable. So if you want to find a Turing machine with n states, we didn't specify how many, so these states are actually dependent on this, the absolute maximum number of ones to a tape before halting. So write as many ones as you can, which could be infinite because the Turing machine is infinite, before stopping. Calculating the maximum number is entirely unpredictable. You would never know how many ones will it write, because you cannot mathematically calculate the absolute maximum number of ones a 5-state Turing machine can print before safely stopping. So you don't know the absolute maximum of ones can print before it stops, because there is no condition for that, isn't it? So